Hello, hello. Yes, all works perfect. So, I one of the topics that's very popular is generics. How many of you are using it? Like, really? Yeah, kind of like not really. Okay, cool, cool, cool. So this is, I think, a great topic for you. So just a quick introduction. I work here in Pure. I'm doing programming for long, long, long. I love metaprogramming, and I think generics are great. Unfortunately, not so much in Go. I will get to it. So, what I'm going to cover, little refresher for those who have never used it, is going to be introduction, although very short one. The stuff that's like not so great, and like what to take home, the essentials to remember, how to use it, what to do, etc. So, before we start, there are all the languages have some assumptions or like approaches, right? And the trade-offs that are being made in all the languages are in like developer time, how long it takes for you to write it, to learn it, etc. Compiler time, how long it builds. It can build forever, it can be super fast, it can be basically almost none, right? And runtime, like how much effort you spend in runtime. So like one of the extremes is, let's say, C++. Like how many of you are familiar with C++? To some degree? Nice. You know that learning it takes forever. You never actually know it, right? Like, like 60% maybe, right? It's very complicated. It takes time. The compiler takes time also, right? To build a large project takes forever in some sense compared to other things. But then runtime, super fast. Everything is optimized to hell, right? It's very hard. It's a benchmark for everyone, right? Like I want to be as fast as C and C++. So it's cool. Another nice example of trade-offs is Python. Easy to learn. Like I guess like everybody can write some Python and it's gonna kind of work because it's like pseudocode. Nice. Developer time, quite easy, safe, right? Compiler, oh, there's not really much of it, right? It translates to a bytecode and runs. So that's super fast. You basically don't have nothing. You just run that code immediately, right? But then in runtime, you pay the price. It's like, oh, types. Oh, this kind of doesn't exist in Python, right? So you have to check in runtime if it can blow up on you, and it's gonna be slow because it's interpreted, right? So Go made certain choices. The choices are developer time. That's optimized for a simple language, a lot of constraints, right? Not many options. There's basically for the most part, it's basic. There's on one way to do it, not more. And there are design challenges in syntax and so on to make sure that the compiler time is also fast, right? So, for example, if you compare the code that it produces compared to, let's say, C++ or Rust, which is another useful language these days, uh, it makes slower code, right? Because it does not want to spend so much time in compile with the compiler, so it doesn't do many of these clever optimizations and so on. We'll get to it, right? So these are the very important assumptions on like how Go works. So it drives like some of the decisions in how generics are implemented. So now a quick refresher on generics. So the discussion actually started in 2011, and it was implemented in 2022. So it took them like what 11 years to figure out like how to do generics, right? So with that, before Go 118, sorry, which was in 22, you are writing code like this, or the advanced people were actually using Go generate and were generating code, right? So some form of generic programming in some sense, right? With generics, it looks like this, right? There is this T, any something, and it kind of like, well, it looks the same, but now it does not have the type in it. It will do something to support more types. That's really cool. How you call it? It's like this, easy, right? What you throw ints, it's gonna work. You throw strings, it's gonna work. Not with all types probably, but maybe it does. Maybe it fails. You never know. So now how it actually works. There's the important part, which is the T that stands for the type parameter. It's like, oh, this is the type. I don't know what it is, but this is the type. And the second thing is the constraint. That's really important. It actually limits, or it actually implies like what interfaces the type T needs to support. So it satisfies this, so it can be used. We get to that. So there are the constraints, the usual one where often you see any. That's basically a constraint saying like it has to be a pointer. It's like nothing. It's like everything, essentially, right? Because the type any is defined like interface. So anything is fine. There's a constraints package that has many of them, and there are some built-ins. Built-ins are, for example, comparable, right? Or there are like ordered, signed. That means like, hey, it's a type that supports some ordering. That's a type that has signed values, right? So it's like not all integers, only the signed ones, right? And so on. So you can define and you can do this to actually limit like what actually needs there. You can also define your own completely, saying like, I have an interface and whatever you send in, it has to support this interface. All right, that's useful. Here, the example is actually it's returning a function, right? That whatever the object has, it has to support this function called foo, and it works. All right, cool. Now we can also have, so that was functions. Now we also have generic types. So you can create a type like a stack or something. It's a nice example because it basically doesn't care what is the type that's being used, but it works with it. Right, that's a nice example. Perfect. Everybody understands this code, more or less? Yep. Cool. Okay. But Go does not like mixing things, right? So this might seem nothing special. This could work. Like, why not? The thing is that I have a struct, which is my type, and then I have a method, right? And or a function with receiver, depends on how you look at it. And it is generic. It says type something. I move on and I want to do something. It's a generic function of a type, right? Doesn't work. Interesting. What do you get is this compiler error, syntax error, right? Method must have no type parameters. Interesting. It has a lot of implications. For example, out of the SDKs, one of them are we using here are in pure lot or in our project has types, but you have to use everything is interface because you cannot do generics, right? So what's going on? So these are now comes the time for the trade-offs, right? If you look at this code, it is a very contrived, like it's kind of like semi-broken example, right? Like nobody would actually use this in real life, but it shows what's the problem. The problem is I create something like the empty struct, right? And I say, oh, there's a function no with the type any, and then I have some other function which actually checks this, all right? If the x, which is type of empty, does support this no interface with ints, with whatever, what is it, string and so on. So the question is, right, if you start generating this code, how is it going to generate it? Does it like go and generate like method for empty, for nop, like for every type possible? Or how, right? That's the issue. Now, quick compiler recap and Go. It's important here, right? Can everybody read this? Cool. Because I'm struggling with my monitor in front of me. So the code goes through a phase which is parsing, and it produces an abstract syntax tree. After that, type checking happens. After that, you get this SSA generation. That's like an intermediate representation, which is very simplified, basically like single static assignments. There's no complicated code anymore, and so on. The problem is that here, the code that you see, like what is going to be in the end, comes with the linker. But that would imply that in order for that to work, you basically go compile everything, figure out, oh, we're missing this, come back and do everything again. And again, possibly, and again, possibly, and again. So that the problem is that it takes way, way more time to actually do this. That's one, right? So all the options are bad. We could do what I described, link time. It's going to be like super slow builds. And in some cases, you can craft a case where this would actually introduce basically endless loop. So very complicated, very slow. The other option that's like used in, for example, in Java is just-in-time compilation. Like, hey, I'm gonna forget it, and then once I need it, I'll compile it. Oh, it makes like the runtime really slow because you don't know, and also the implementation is gonna be spaghetti code, really complicated. Or reflection, another nice way how to do it, but takes forever, right? So that would not make produce a fast code at all. The other option is like, you know what, like, will not support interfaces, because that's the real problem, right? Like we say, like, hey, if you want to use this, the only thing you could use like instance stuff. It's like, yeah, but then you're kind of like killing one of the good features of Go in that case. So it doesn't make sense. Obviously, there's an option just not support it at all, and say, hey, we don't do this at all. And if you need something like this, you make a function that you pass the parameter in, right? It works. It does not. It solves the problem with the compiler. It knows it upfront. All good. It doesn't really work well for the SDKs and stuff like that. So yeah. I mean, I can live with that. Okay, then another thing that generics bring is this nice code. Like, anybody sees any problem? To me, it looks really good. It's like, I would go and ship it, no problem, right? What do you mean? Oh, it's like implied it's integer, right? Yeah, it's implied it's integer. Yeah, okay. So this would be okay, right? Like I'm gonna like say, hey, ship it. Hey, compiler. Okay. It says that the operation, the comparison is not actually working. Yeah, because you need to know what comparable means. The thing is that the comparable means, oh, it supports like equal sign. Everything else, no, right? You do for equality. It's not ordered. Doesn't say anything about ordering. That's why it's very useful to know the constraints, right? But you could say like, hey, but it's int. That's ordered. That should work. Yeah, we're going back to the compiler phases, right? So again, the type checking when it happens quite early on. Like, yeah, when I'm seeing this function, I'm like checking, yeah, all good. But then you're in the function, you're using something that was not supported. Maybe later you instantiate the version which is fine, but it's too late. So that's why you get these errors. Learn about the constraints. It's really important to know them if you're using generics. They also help a lot. Okay. Other cool thing is generics make code slower and significantly slower sometimes, right? I'll give you a few seconds to read the code, but basically there's an interface called valuer. There's some function called value that needs to support, right? The interface. And then I have my struct, and that supports actually implements the interface value. And I have a code that actually goes through this, and you see the constraint, it's valuer, like only these things can be supported. All good there, right? You can also write the same code and call it like, not the generic one, but sum it and put and really insist on the instruct, the same thing, implementing the same thing. The code would look the same in the non-generic. Fate would look the same if you compare it. You see it to the benchmark. Quite bad, right? Huge difference. What the hell? So the major problem is something that's in essence called like type erasure. What that means is that because the compiler at the point where it's working does not know, oh, this could be like basically anything. It's a pointer, right? So it does not produce a code that's optimized for whatever you're sending in, but it's building a generic one. And because it cannot really do much clever things at the beginning, it just assumes its interface. So, which leads to everything is on heap, right? Nothing is on stack. It cannot cache optimize things. And like a lot of the things that are later available in the like later phases of the compiler, they disappear, right? Because there's a, you know, like the inlining and all this disappears. So that's why it makes it slower. The problem actually is that in other languages, like let's say C++ or Rust or, you know, many others, the thing that the compilers do is something that's called monomorphization, and that actually is a clever way how to say, oh, it basically generates functions for each type that's being used, like specifically, nothing generic. It's like you shove it int, it will produce a code for int, for string, for whatever, right? Go is not doing that because, as I mentioned before, the phases. It would imply that, oh, you will go like back and forth and back and forth. It would require a lot of changes in Go, and it would make it way slower. So they came up with this idea that, hey, we could do the monomorphization of some sorts based on whatever garbage collector shape that thing has. So it's kind of like strangely middle ground. It's not totally generic code, like, oh, I'm assuming it's pointers everything, I dereference everything, and just one code for everything. But if you're sending all ints, it will produce some code that's like specific for all the ints. But if you put something else with the pointer, it will use interface. So you get 3, 4, 5 different, maybe, possibly, depending on what you send roughly. But it's like halfway there. So very often it produces a slower thing because you're using something, then a lot of the optimizations can happen later. So, and then some people might get confused, but generics are not interfaces. I've seen this happen. And it's like, oh, I use generics, I don't use interfaces because, like, you know, like for some people it might be causing confusion, right? But I think that the important thing is like, if you don't know what to use, think of it this way: interfaces are for behaviors. Basically, you want some function to support. You want interface. If you want to have a abstraction over data types, you use generics. Simple, breaks like 99% of time, right? I think that, but that's all the big things I think that are wrong. But like, should I use generics at all, even like in Go, right? Like, short answer is yes, but, right? You learn a few things. So one is, yes, it's really good for data structures. That's the exact use case where it shines the best, works the best. It solves a lot of problems, right? Like the generic data structures for, you know, like maps, hashes, whatever, stacks. Very good, very good. You don't hit any of the issues, actually. Do use the constraints because actually they drive and they help the compiler to figure out like what is possible and therefore produce better code. So don't do any if you don't have to. Right, just, well, and that's the next point. If you're passing interface, you're gonna kill the performance anyway, so don't bother with constraints. Does not bring any value, right? So maybe just don't do it. And then, you know, if you have interfaces in your API, it's fine. You don't have to make it like use generics in that point. They're really good. It's fine. As long as it's not data structures, then move on and do it in generics. But otherwise, keep it as it is. Cool. And I think that's all I wanted to say today. Right. Oh, actually, I forgot. Generate. Generate is still good. There are still use cases, like especially when you're for performance use case, then generating your own code, like handwritten, for the types you need and so on, still is good. Works pretty well. So don't forget that this is still an option. You may not like it, but it's an option. Okay, thank you.